in the logistic regression, we are trying to, let's start with an example. So the example is the following. We have a word that can be used in two different, the same word can be used with two different variants. One is which is dialectical, and the other one which is, I don't know, formal. Now it doesn't, I mean, the same word can be used in these two forms, and you want to do a statistical analysis on which form is most is used more or whatever. We start collecting data. Let's collect the simplest data that we can collect, which is, for instance, we ask some we ask some people to say a sentence, and we observe which variant of the word they used. So at the end of the day, we have some data which is done in the following way. So have a form which is can be either dialectical or formal, and let's say let's put some randomly generated data. At the end of the day, you will have a data set which is this form. So, and simply for saving it as a factor, let's impose that is factor. So this is some randomly, I mean, this could be the output of your experiment. And now you want to predict. So to predict the probability that a person will say the dialectical, which variant say the dialectical variant. So this is a very simple task, and I mean the model here is usually the same. I mean every person it's always the same. Every person says the variant that each person says is independent from the other people, from what the other people said, and what to do now? Well, first of all, we can define this variable yi, which is first the task. The task is to predict the output of the variable. Let's call it tilde y, which is the form uh, said by the person. Um, well, let's define. The first thing is to define a numeric variable. So yi is a dummy variable which takes the values 0 and 1. Um, um, let's say, okay, let's call it is formal, this variable. Is formal I is equal to 1 if the I person said the formal variant. And 0 otherwise. So now, and the model is that y these yi's are independent Bernoullian of a parameter p. Do you remember what Bernoullian means? So it's a variable which can take only two values, 0 or 1. So the parameter p means the probability that yi is equal to 1. So that the probability that the person will say the formal variant. Okay, how to estimate what so let me define first this variable is formal, so that we will have it on saved in the computer. So how to do it is formal is equal to, here we have a factor, is formal will be equal to, so if I write something like form equal to dialectical, what do you think it will give me, the computer? Because that R works with blocks. So form is a vector, dialectical is recycled, so it's a vector dialectical. So it's like, and this double equal is a question to the computer. So it's not an assignment, but we are asking if this vector form is equal to the vector of only dialectical. And the output, the computer can reply only with true or false. So when it is true, it will return as true, and false otherwise. So true will be in the positions where there is a dialectical, false when it's not dialectical, which in this case means that is formal. So let me use formal here instead of dialectical. And now the computer, if we impose them to be numbers, will use put in false, we'll use a 0 for the false, and 1 for the true. So this vector will be a vector of zeros of ones. Sorry, 0 when is. Sorry, let me check it again. Yes, 0 when it's false, 1 when it's true. So let's plot what we defined form and is formal. I have to download tidyverse. Sorry, to attach tidyverse. So we defined, I mean, these are the two variables, form and the dummy variable, which I created, you putting zeros in dialectical and 1 in what is form. Is dummy because these are not really numbers, are simply placeholders, if you want. I mean, now, what is the estimate that you would do for the parameter p? So this should be, I mean, you have only this data. If you have to guess something, how would you the parameter p, recall that is the probability that a randomly chosen person says what was the formal variant. So and I took only 1, 2, 3, 4, 9 people and checked whether they say the dialectical or the formal word. So I mean, to estimate the parameter, what would you do? This is like coin tosses. The model is the same. That's why we did them a lot. So if you want to see the parameter of a coin, maybe it's unbalanced. So you have to toss it many times and record how many times it, it gives heads or tails. Yes, the number of ones divided or divided the total number of. So a good guess. I mean, if here we see only the dialectical for version, we would say, okay, on. I mean, not surely, but we would we would regard the probability of saying dialectical form much higher. The parameter p depends on these observations. So a good estimate is the number of ones divided by the total number of answers. So would be this one. The mean of the vector is formal. Which is 0.5, which is not really 1, 2, 3, 4, 5, 6, 7, 8. Yes, it makes sense. Okay, actually, I guess that this is the thing that the logistic regression will give us in this case, but assume now that we make a, I mean, this is a stupid experiment, so we make a more precise experiment, and we record instead that only the form they used, also the age. I mean, we are doing an experiment, so we can also, I don't know, record like variables that I mean, I don't know, maybe about the subject, like it could be old, young, so we can record his age, maybe the mood he was when he was doing the test, or also variables that concern like the form of the sentence. I mean, there are many different sentences. Maybe the word appeared as I don't know, as a main part of the sentence or as at the end, I don't know. There are many variables that can be taken into account. Let's assume that we also record the age of the subject. Let's assume that let's perform a more precise experiment, and let's collect also the age of this. So now we will have also another row in the data, and the row will be numbers that I won't put. I will put that the dialectical form was used mostly by young people. So let me say 20, 40, 50, 10, 30. I don't know if 30 is young or I don't know. Then 55, 45, 53. Let's say this, and let's put it into a vector together with the observation of the form, this form. And let's look at the data. So this could be like the output of your experiment. Why is taking so long? It's having some problems, so Uh, okay, so this is the data, and let's plot it also. So you see, uh, this is your bivariate observation. On the y-axis, you have only two possible choices. On the x-axis, you have an age, so it's a continuous variable. Uh, so let's do a linear regression, for instance, and let's see what problems may arise from a linear regression. So the linear regression, as usual, can be done with ggplot, and uh, so we on the x-axis we have the age, on the y-axis you have this variable is formal. Um, then we plot the points, and we do a linear regression. So we try to predict if the answer was formal, the variant was formal or not using the age. So let's see what do we get. Okay, let me remove the standard error. So this area, which is more shaded, this shaded area is because the is the error that, I mean, the line, since there are very little data, the regression line, there is some uncertainty. I mean, so it's like, well, we obtain this line, but maybe if we have some more data, it will change. It's more likely that the line passes into this area. But so if we add more data, this area shrinks. But we will simply remove this area by and put under the rug this problem. Uh, and now we have this estimate. So what's the problem if we do this? How could we interpret, like, recall that the linear model tells us that the variable is formal. It's equal to, I don't know, beta 0 plus, so 20, if the slope is like 30, so let's say 30 times age uh, minus 20. So how would you interpret this uh, this line? Um, So is formally is a variable which is either 0 or 1. So here the line gives you values that are not only 0 and 1. And moreover, they will be like most of the time they will be less than 0 here or greater, or they will be greater than 1. So and it's not even clear what those a prediction which is not 0 or 1 mean. I mean, um, so this is one problem, for instance. Uh, can take only 0, 1 values. Uh, 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 um, so this is one problem. So how can we interpret this value? Um, so you see a prediction based on a line, it's bad because you should have either 0 or 1. So maybe we could interpret like when it is below here, we interpret this as at 0. And yes, exactly, likeliness or probability. So we can interpret it as a probability of being formal or direct. So, for instance, here the probability would be so. So the idea is right. We interpret we can interpret it as if it were a probability, but then here we have a problem that a probability cannot be greater than 1 or smaller than 0. So this model is not a good one, but the hint of considering it as probability is a good one. So we will do this one, and the idea is the following. Uh, so uh, we have now some observations. Uh, x1, y1, which is equal to little x y1 until uh, have n observations of age and variant of thing of the word that we say that the informant used. So, the y's the y is a Bernoullian, sorry, a Bernoullian random variable. Uh, so it is a Bernoullian random variable, and we want to estimate uh, to estimate the parameter p. Now we have before we had like no x, so we estimated p using the mean. Now we want to use also the information given by x. So in general, y conditioned on the observation x equal to x, so is a Bernoullian random variable of parameter p of x. So here is a little bit a tricky point. Do you see what is what I'm doing? So we can compute, we can compute the probability, for instance, this p would be equal to the probability that y is equal to 1. But this p of x, we can compute also this p of x, which is the probability that y is equal to 1, given that x is equal to x. So for instance, if we are observing also the age, maybe this mean changes. So it's because y and x are dependent. So if I take a subject, I know some stuff about it, maybe the mean of y also changes. So I'm taking, so the relation between these two, if you want, maybe I can write the relation between p and p of x. So the probability by the total probability formula, the probability that y is equal to 1 is equal to the integral, the probability that y is equal to 1 given x is equal to x times the probability that x is equal to x. So this is written very badly in a mathematical way, but it's like the total probability formula. We, instead of the summation, there is an integral. So this is the relation between p and p of x. I mean, you don't need to know that, but I mean, is it clear that this, since y and x are dependent, the mean of y, the parameter, can depend on x. So you observe an older man, maybe it's more likely that he uses a formal. Is it clear, or should I? So the parameter p depends on. So for instance, what one would do, like to estimate this p of x, if you were to perform, like if you had an infinite amount of money, you go through all the Moscow citizens, you call them, you take the ones which have the same age, like you fix 35 years old, and you take like 35 minus 1 month, 35 plus 1 month, and you consider only them. And then you perform the experiment only with them, and you will obtain this parameter p of 35, like. And if you take another age, it will change. So, I mean, not maybe not, but in principle, it will depend. This p depends on. Uh, so, I mean, does it make sense? Uh, then, of course, if you choose randomly a person, um, okay, the total p between all the ages will be somewhat okay. How many people there is that there are that have 35 years old? I don't know, 5%, and so this parameter p gets weighted by the number of people that have 35 years old, and you do this. That's the reason of this integral, of this relation. So as the total p will be like a sum of all the p's of different ages weighted differently. So, so I don't know if the above formula, so to estimate having an infinite amount of money, we to estimate p of 35, we would perform the experiment using informants whose age is, say, 35 plus minus that 0.1 plus minus 0.1. And in general, and we can repeat it for different ages, and the p of x will change. If we want to recover the total p, I mean, this is not necessary, because why you should want to recover the total p, but because p of x is a more precise information, uh, what do we do? Well, we use the formula, this integral formula, which tells that the real p is a sum of, not the real p, sorry, the total p. Total p obtained by randomly selecting people without looking at their ages is a sum of the other p of all the p's of x weighted the number of people with that age, which is this one. But this, I mean, this is a good, I mean, uh, this is a result of probability theory. This one, this integral formula. So you don't need to do it. But in general, you simply need to understand that if we observe x, we can be more precise on the parameter, and then we can recover the parameter simply by integration. But so what do you want to know is, I mean, and I want to know if you understood it, if that is that this parameter p depends on the age in general. So for instance, so there's two categorical variables. I don't know, the fact of wearing a hat. If you go to older people, they will be more likely this p will be higher. Yes, I know. If you plot it, maybe there is some. I mean, some people who went through the I don't know. I don't know. There was a year that the hat was really popular, so you will see spikes in this p. I mean, it will be. It won't be constant with the age. Then, if you take a random person, not considering the age, of course, the parameter gets a little bit weighted because. But this is a probability result, so it's not easy. It's this integral formula, which is basically the total probability formula. Um, but do you understand that this p varies with the age? Okay, that's uh, that's good. So we want to estimate p of x. What do we do? Well, p of x is a number between 0 and 1. And we have seen that we want to estimate p of x with a simple function, using a simple function. But we have seen that a line doesn't really, is not really a good stuff, because uh, sorry, it's not really a good stuff, because we go here and p would be really negative or positive or greater than 1. So, but a line is not a good choice. We will use a line, but not on the piece. So the trick is to transform uh, p of x into a number that can vary between minus infinity and plus infinity. So we look for a transformation f that goes from 0 to 1 to minus infinity plus infinity. And we want to estimate f of p of x with a line. So this now the problem is to find this f. So what do we do? So first of all, we consider the odds. What are the odds? Um, so let A be an event of probability must be P of A. The odds of A are defined by this formula. Is the probability of A divided by the probability of the complementary of A. Um, let's call the odds Q, for instance. I don't know if they have a better name. Uh, and they can also be written in the following way. So this is a definition. Um, so let's for a moment look at it, and I don't know if the odds are 1 to 1. What is the probability of the event A? Like they are even common in the language, the odds. Like if the odds are in your favor, let's say if the odds uh, are positive, uh, what does it mean, for instance? Like if the odds are 1 to 1 equal to 1, what does it mean? And then if the odds, if P of A is equal to 0, what are the odds? And the if the probability of A is equal to 1, what are the odds? These are good questions to look at. So the first one you could also, I mean, probably is called chance in Russian, I don't know, but I mean, it's common like sense. If the odds are in your favor, what is the probability of the event? So sorry, not positive, greater than 1. Sorry. Um, if the odds are in your favor, are greater than 1. So greater, like for instance, 2 to 1. Hmm? Uh, yes, it means that the probability of A is greater than, so let me write it, let me prove it that the probability of A divided by 1 minus the probability of A is greater than 1/2. Sorry, 1, sorry. This means that the probability of A is greater than 1 minus the probability of A, which means that the probability of A is greater than 1. So that the odds are in your favor means that like 2 to 1 means that the probability of A is greater than the probability of the complementary, that A doesn't happen. So if you're like that A happens, if you like the fact that A happens, then like the odds are in your favor because it's more likely A to happen than it's complementary. So this is only algebra, so it is a function. The odds of and for instance, if the odds are 1, it means that the probability of A is equal to 1/2. If the probability of A is 0, you plug it here, the odds are 0. If the probability of A is 1, then the odds are plus infinity, because 1 divided by 0 by a positive 0 is plus infinity. Uh, so, for instance, if the odds are 2 to 1, let's see what happens. If this is equal to 2 divided by 1, it means that the probability of A will happen twice more likely than the probability of its complementary. So this is why they're usually put in this form. So it means that the probability of A is twice as likely the probability that the complementary happens. And this means that the probability of A here is equal to 2 divided by 3, something like that. So you see, 2 divided by 3 is 2 times 1 divided by 3. So it's um, okay. So maybe let's plot the function. So yes, let's plot this function. So p, let's take p from 0 to 1. A vector that goes from 0 to 1 separated by so maybe it's better, it's simpler to see what is p by looking at its values. So it starts from 0 and it contains all the points from 0 to 1 separated by this width. So we can compute the odds. The odds is the function of p is p divided by 1 minus p, and save it into the vector odds. And we can plot p. To each p, we associate the odds. Okay, so you see, when p is almost 1, this thing explodes to plus infinity. And when p is equal to 0, this thing is 0. So the odds live in 0 plus infinity. That's this. You see the odds are on the vertical axis, and they don't take negative values, but only positive values. So, that's it. And to each odd q, the probability that gives that odd is given by E is equal to Q divided by 1 plus Q. So this is the inverse of the function. Before so okay, these are the odds. We are still not there because we wanted a vector that was in the whole line, not only in the positive numbers. So we need a transformation that sends the positives to the whole line. So we need a transformation that sends minus infinity, 0 plus infinity to minus infinity plus infinity. So because the odds because the odds only send 0, 1 to 0 plus infinity. And what is this transformation? Well, the logarithm. The log does its job because let's look at this function, this logarithm. Curve log. Okay, you see it takes the whole positive line and it okay, curve log x lim is equal to say -10 -2 to 10 and y lim equal to -10 to 10. Let's see better this function. okay, this is the logarithm. Now at a certain point it stops, but you should think that there is, so let me plot also the vertical axis. It's a very, I mean, uh, vector, um, it goes from zero, it sends a number that goes from zero to plus infinity to minus infinity to plus infinity. Now, it's a very strange function because it's really, it goes to plus infinity really, really slowly, and in zero, it goes to minus infinity really, really, when it's really, really slowly. So, but however, the logarithm of zero is minus infinity, even if here you don't see it. So this is the function that we want. Now, you should tell me, I can explain better what the logarithms are, or I can go on and I mean, do you remember that what are logarithms? I mean, the inverse of the exponential. So maybe let me simply recall something. Yes. Mm, so if we have the exponential of y, which by the way is this function, uh, uh, um, okay, is this function here, which grows very, very rapidly, and when x is when x is big, and when goes to minus infinity, is zero almost immediately. But actually, it's not zero. It's never zero. So even if you cannot see from this graph, and how is defined the logarithm? Well, the logarithm is the logarithm of x if e of y is equal to x, uh, then the logarithm of x is equal to 1. So the logarithm of a number, let's take a number a, is defined as is the number b such that e to the power b is equal to 8, something like that. The definition of inverse. Uh, what how is this? I mean, it's a little bit tricky because uh, but graphically it's really immediate to see what it is. Well, it's not immediate, but graphically can be defined in this way. So maybe let me plot it like Um, let me take a particular x, like 2, and a particular y, which is the exponential of 2. And let me plot this function exponential with some segments. The first one, which goes from the x particular to the value of on the graph. So a little bit should work. Let me see. Again. Um, hmm, why is not plotting the function? I need to look for pixel. Uh, um, I don't know. Um, maybe I need some aesthetic. So, or data, no. Data equal to tip expert. No, 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 no. Well, maybe I will do it in the break. I will do. So the logarithm is a function which inverts the exponential. So that in particular the logarithm of the exponential of y is equal to y. Mm, simply because or the exponential of the logarithm of x is equal to x. These are the properties of the inverse functions. And what we are looking for is the log of the odds. So of p divided by 1 minus p. This is a number which is in minus infinity, but to plus infinity. Why? Because this p divided by 1 minus p was in 0 plus infinity. This logarithm sends 0 to minus infinity, so stretch, and plus infinity to plus infinity. So why? Because logarithm of 0 is equal to minus infinity equal to minus infinity, and log of plus infinity is equal to plus infinity. We can see it from here. So this is the exponential, this one. I mean, you cannot see it from here because there is a joke that a logarithm is a constant, but the logarithm, when x is big, it goes to plus infinity. So even if it will reach 10 very, very far away, it will reach 10 like when at the point e to the power 10, because and e to the power 10 is really huge. So it's almost a constant, but it's not a constant. It goes to plus infinity. And in zero, the same thing. I mean, you really need to be very next to zero to see minus infinity. So, but this is true, even if it doesn't seem. So, and we can, at the end of the day, let me finish because it's not the most interesting part of this discussion. We have this function, which is the logarithm of p of x divided by 1 minus p of x. And this is a function, is the function f we were looking for. F of p of x. Maybe it's better to call it f of p equal to the fraction, 32 the logarithm of p divided by 1 minus p. And this function has an inverse, which is sigma. The sigmoid function, which is such that p is equal to sigma of f of p. And the definition of, say, f sigma of q is equal to 1 divided by 1 plus the exponential of minus q, for the e to the power minus q. So we have these two functions. So maybe we can take a break and continue. Yes, yes, maybe it's better because this is not a, I mean, it's important, but it's only computation. So let's take a break and continue later. Okay, we were saying that we have some observations uh, of variables x and y. So um, these variables are, we were making in the example we were discussing, this x is the age, and y is like a categorical variable. The categorical variable which describes, like we are making an experiment in which two forms of the word of a word can be used, one formal, one dialectical, and y is simply tells you is one when the form used is a formal, zero if it is dialectical. We want to estimate the parameter of y, because y can take only the values 0 and 1, and we want to estimate p of x, which is the probability that y is equal to 1 given that x is equal to x. And we want to do it with a simple function. So we would like to do it with a linear function, but the problem is that, so we want to estimate this with a simple function. But a line is not a good thing, because why? Because p of x is in 0 and 1, while beta 0 plus beta 1 x is in minus infinity plus infinity. And in the first half of the lecture, we have found a transformation which is the log of the odds. So f of p of x is equal to the logarithm of p divided 1 minus p. Is the log of the odds and when P is in 0 and 1, f of P is in minus infinity plus infinity. So this is the function that we want to estimate with a line. So we make the following answers. Which is f of p of x is equal to beta 0 plus beta 1 x. So this function f has also an inverse. The inverse is the sigmoid function. Which is 1 divided by 1 plus the exponential of minus q. So at the end of the day, we look for p of x in the following form. As sigma of beta 0 plus beta 1 times x. So if f has this form here, and we want it to be simple, we have to use a line to estimate f of p of x, then p of x, we apply the inverse in both sides, and p of x has to be of this form. Sigma is the sigmoid function, it's famous in machine learning, and it is. And now we are going to plot this function. I mean, let's do plot. So now I have to remember the code because I don't remember it actually. So it was this one. So this library allows uh, plot something, allows us to plot as this function p of x and to vary beta 0 and beta 1 interactively with a graphic which is really like Windows 95, but it's actually good. So we I'm defining this sigmoid function here, which I call here G. Maybe it's better to call it sigmoid. And then I plot this sigmoid using beta 0 and beta 1 as parameters, which are in this variable. So let me. Okay, maybe let's do it. Okay. Now I don't see the interactive part, so let me do it on the command line. So okay. So no, okay. Now we are. So beta zero is simply a translation uh, the all this function. You see, this function is in between 0 and 1. Let's take beta 1 positive, for instance, 10, and let's vary beta 0. So beta 0, as it goes, as beta 0 gets bigger, the function gets all shifted to the left. Uh, so maybe we can see better with small betas, beta 1. So you see, I'm simply shifting data, the graph with beta 0. Instead, with beta 1, makes the transition between 0 and 1 very sharper and sharper. You see, if I take beta 1 equal to 1, to 10, sorry, it will be almost a vertical line between 0 and 1. And if I take it smaller, it will be less sharp. 0, it will be a constant, this. Uh, but you see, and the beta 1 negative will be on the other side. I mean, and if I put it very, take beta 1 to be minus 10, it's almost vertical, this transition between. So, can you see it from there? Ah, this. Okay, so this is how it depends on beta 0 and beta 1. So there's no easy interpretation of these parameters, like was in the linear regression, in which beta 1 was the you increase the x, and beta 1 is the rate of how much it increases beta y. Here, there is no such thing, but at least we can tell that if beta 1 is positive, it means that when like in the case of the ages, age and the formal, it means that when the age increases, the word that we use is, is, is more likely to be formal if beta 1 is positive, and beta 0 is a translation of the function. So this is simply how to play with this function, but I mean, we can see it. I wanted to also to do the way in which we choose this beta 0 and beta 1, which is the maximum likelihood function. But I guess there is no time to do that. I mean, and it's only mathematics, so it's only computations. It's interesting, but maybe it's better to see some examples. So now, yes, now the point the point, the question now is how to choose beta 0 and beta 1. I have written it in the notes, so if you're interested in it, you can read them. But there's no time now. The way of choosing them is the maximum is via the maximum likelihood estimator. And let's go to the examples. So first, this is called the logistic regression. So I don't know if I said it. When once we fix the parameters, we have made a logistic regression. Okay, let's try with some data which I took from I stole from the GitHub page of George Moroz, in which he collected many languages, and I don't know really what adjectives are, but I don't know. Can you tell me if a language has adjectives, what does it mean?
So it's where before making an explosion, you add the stop.
Okay, okay. And this data contains the many languages, and the number of consonants of each language, and if it has adjectives or not. So I guess if it has more consonants, it will be more likely that it has less adjectives, I guess, or not. Okay, no, it's the converse. So my linguistic intuition is not so good. But what's the point of intuition if we can do a logistic regression? I'm joking, but we can try to predict the likelihood of a language to have adjectives using the number of consonants. So first we transform the adjectives into a variable which is 0 and 1. So again, these adjectives is the vector of yes or no. That is no if the language doesn't have adjectives. Now we make a question. This question is this vector equal to the vector yes. So this will give us true when there is a yes, no when there is a no. So again, R is a vector language, so we are making this operation equal equal will act on each component of the vector, and this vector, this yes, will be recycled. So the program will make a vector of yes, of only yes, 27 yes, and it will compare each component of these two vectors, and it will return false if if the component I mean the question answers negatively and true otherwise, and we can take and we can make them numbers by imposing them to be numbers. So a false is 0 and a true is 1. So now we can save this variable into is so now maybe let's use some tidyverse stuff. So we define A as adjectives where we mutate these adjectives and make a new column is adjective where we save this vector here. And we will, I don't remember here the syntaxes, so let me look for it. So I want to keep not only the unused columns. So I will eliminate the old, delete the old adjective. So keep is equal unused. And this will give me the same data set with this column, which is modified from 0, 1, from a yes or no to 0 and 1. Atomic vectors. Ah, sorry. Okay. Now that we have our good variable, which is made of 0 and 1s, we can do a logistic regression. Let me first do it with ggplot, so we will see it immediately. So the data is equal to the adjectives. The statics is we have to put on the x-axis the number of consonants. And then the y-axis we need to put whether there are adjectives or not. And then to do a linear regression, we use the usual command geom smooth. But now the method is not a linear method; it's a generalized linear method. GLM. Generalized why? Because it's not linear, because P of X is not linear, but the log of the odds is linear in the log of the odds, so it's generalized linear model. So it's not really, it's, it's a generalized linear model. And have to pass the arguments the method uses, because there are many generalized linear model, and we use a binomial one. So let me see what errors are in this, what are the errors in this code. Methods args, of course, is not a good way, so let me look for it. Uh, so the method is a generalized one, generalized model. Method args equal to list. Maybe I have to use statsmove. Ah, no, okay, sorry, I have also to plot the points. Um, and then what I want to remove also the standard error. So this shaded area, and I have to put also formula. Formula, I want to predict y using x. This is the code with which you can do a logistic regression. And you see, this is the result. I mean, makes sense. It's a good prediction in this case. I mean, of course, now we are not predicting, we are just fitting, but it fits pretty well. Now, let's have a look. So, yes, the more consonants are there, the more the likelihood of having ejectives. So, let's also look at what the model, what can we do without using ggplot. So the generalized linear model of the data is equal to A, and we want to predict the column is ejective using the number of consonants. And the method, the family is of the binomial method. So family. And let's see what this function gives to us. So we can see that there are some estimate of the coefficients, like the intercept and the slope, so, and the slope, yes. These are the beta 0 and the beta 1. There are 26 degrees of freedom because there should be like, I guess, 28 languages in this dataset. Let me, I know, 27. And 25 residuals. Variance and residual variance. Okay, these are some these are some data. Maybe uh, I will explain better what this AIC means, but another time. This time, simply let's write what the expression for P. P of x is equal to the sigmoid function of beta 0 plus beta 1 x times x, so of minus 9.2.9 plus 0.38, so 0.4 x. Which we can plot actually, so let's check that it's the same plot. So minus 9.9 plus 0.4 times x. Let's check that it's the same line. Sigmoid. Okay, these were the. Okay, this is. Okay. The y-axis is really, really concentrated, so we cannot see anything from here. So, which makes sense because I have to set the limits of the axis. So, say the number of consonants will be between 10 and 40, and y between -1 and 3. Let's make this choice. The lengths of x and y differ. Y lim. And of course, I have to sample from 10 to 40. And it should be this one, but let me type it. Okay, this is the same function. Like at 25, it has this point of inflection, which is yes. So this is the output of the logistic regression. Simply, quite simple. Now, what can be done? I can do more examples and introduce you to this Dracor corpus, which is actually a nice nice corpus. So, um, it contains the data of many dramas in Russian language, in Russian, German, and Italian language. So, how to download it? There was the professor of 2 years ago, which is Ivan Posniakov, which was like developing a package for reading and skimming through this corpus. Developed, I guess, together with other people, a package to use for working with this corpus. Now let me remember how you. Let me tell you how you can download it. Because it is on his GitHub page. Um, so this one. So to install from GitHub, you need this DevTools package, and with this you can download this package, which Ivan Posniakov, the professor of 2 years ago, developed. So with DevTools, you can install from GitHub. With install GitHub, you can you install this package AirDraco, and then we can use this package to get the data. So AirDraco get Dracor uh, I guess get Dracor. Okay, let's work with the Russian corpus. So we take this Russian corpora and we save it into Russian. And now we can look at some data. So it's huge, so it requires a little bit of time and to download. And let's look what does it have this data. So what do we use to skim through some data? Well, we can use, there are many functions. We can either use head to plot the first lines of this data set. We can use summary, we can use skimmer. So for instance, there are 60 columns, so it is huge. There is the play name here, the year, when it was first, I guess, played, the title in Cyrillic, the title in English, the subtitles, the authors, Wikipedia source, and then there start to be some interesting statistics like the network size, which I don't know what it means actually. Should read it. But if you go to the website, you can read what all these columns mean. There is the genre of the play. It could be a comedy, a tragedy, or a tragicomedy. The size, the density, the clustering, I guess, the clustering of the authors, so of the not of the actors, and the characters in the play. So if maybe there are two different stories in the same play, so that and the actors don't really play, don't really interplay between them, and there are two clusters of act. I mean, I guess it would be something like that. The percentage of clustering. And then there are other statistics. So number of female speakers, number of speakers. So, and I don't know what one can try to predict here. Mm, we can try to see the number, I don't know, we can try to see like to plot the number of female speakers and the genre of the play. So let's try to do that. I don't know what it will. Let's plot. So Russian speaker, number of speakers female, and the comedy. Ah, yes, I need to remove the nota numbers, but let's for a moment forget about it. The normalized gender. Um, okay, yes, I need to do some. Let me use some tidier stuff. So first we select only the columns which we are interested in. So we select a number of speakers female. Then we select also the normalized gender. We remove the nota numbers. Okay. We drop nota A. Then we transform the column of normalized gender into a column of 0 and 1. So mutate is comedy is equal to uh, as numeric of normalized gender equal to comedy. This will put a 1 if it is a comedy, a 0 if it is a tragedy, because there are no tragicomedies in this data set actually. And let's try to see, and let's keep only the unused column. And let's try to ggplot it. So uh, the point, do you know what does it mean? The point is simply I'm taking the output of the previous code and I'm putting it where the point is. Then let's plot the points. This should be, I have a feeling that this is right and doesn't give me errors. It won't give me errors. Okay. What normalized gender not found. I changed its name in its comedy. Yes, of course. Okay. It seems that a logistic regression wouldn't be too much of use here. Let's try with male speakers. Mm, mm, Even here is not so. So on the if it is a comedy, the number of speakers, or if it is a tragedy, doesn't seem to matter. So let's um, yes, there are tragedies with 80 number of speakers, which is insane. But okay, there are also comedies with uh, oof, I don't know what can be where we can use. Do you have any idea of what logistic regression we can do? So I simply plot the call names. So let me the names of the columns are the following. Uh, so the variables which are um, categorical are like don't know, not so many. Like the genre of the if it is a comedy or a tragedy, then the year is also a. We could try to don't know deduce the year of the when it was published. We divide like on two blocks, like I don't know, 19th century dramas and 20th century drama, and we can try to predict in which century they belong using I don't know the number of speakers. Or, mm, mm, yes, we can try to do that, or simply we can go to another argument to another topic of I don't know, I don't know. Mm. Mm. But I mean, there is a huge amount of data here, so it's a nice corpus. And there is also the German one, which is even bigger. Of how many uh, rows are there? How many plays? How many dramas? 212, which is not too many, but it's a lot actually. And uh, instead, the German one, uh, let's try to see it. Uh, so it's requiring a little bit more. So you see that there are 700 plays. So it's a lot in the German corpus. Maybe let's try to do the same with the German, see if there is some difference. So let's substitute instead of Russian, German, and let's try it. Okay. However, okay. Once in a while there is a tragedy with 800 speakers, which maybe is the Faust. I don't know. No, I don't know. Let, let me just simply see which comedy is this one. So uh, the number of speakers is like 800. So German, let me uh, filter it with using like the number of speakers uh, number of speakers, sorry, is greater than 70. It is I don't know what it's called, call names. Select play name. Mm, which I don't know what is this. So I don't know if you know, but I don't know it. The name and author. Mm, uh, authors. Uh, it's a list of four. Sorry, I will Google for it. So you see, actually, it's not. I mean, skimming through this data set is not a trivial stuff. I mean, it may seem easy, but makes it easy. It makes it easy. Otherwise, it's a problem. I mean, looking through. So this display is actually uh, the last days of mankind. Mankind, okay, of Kraus. It's a satirical play. Okay, nice to know. I didn't know it. Um, and it has 800 speakers. So okay, doing statistics with this kind of stuff, I mean, could be difficult actually. Well, let's look at the number of speakers in total. Okay, so no. Uh, well, I think for today, I mean, I didn't find any variable which it's we can do. I mean, we can try to split to look at the year at the century when it was published, but I mean, you can do it by yourself if you're interested in. No, seems probably it won't be, it would be useless to do a logistic regression. So maybe for today it's, I don't know. Do you have any questions? No? So, ah, do you have any questions?